Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In today's session, our aim is to solve a general nonlinear programming problem involving inequality constraints. We have seen that a nonlinear programming problem with equality constraints can be solved using Lagrangian multiplier method. Now, if we convert a NLPP with inequality constraints into equality constraints, then by known method we can easily obtain the solution for general nonlinear programming problem with inequality constraint. In particular, in this session we consider a nonlinear programming problem with single inequality constraints. Consider the nonlinear programming problem of maximizing z equal to f of x1 x2 xn subject to the constraints g of x1 x2 xn less than or equal to c, where c is a constant and the decision variable x1 x2 xn are non-negative. So, the given NLPP involving single inequality constraints. Now, if we remodify this nonlinear programming problem with inequality constraints into equality constraints, then by known method we can easily obtain the solution for this problem. Now, if we introduce h of x1, x2, etc., 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 xn as g of x1, x2, etc., xn minus c, then this constraint becomes h of x1, x2, etc., xn less than or equal to 0. So, by taking g of x1, x2, xn minus c as h of x1, x2, xn, then the given constraints g of x1, x2, xn less than or equal to c becomes h of x1, x2, xn less than or equal to 0. By this introduction of this function, now the given nonlinear programming problem can be written as optimizing z equal to f of x subject to the constraints h of x less than or equal to 0 and x greater than or equal to 0. So, by introduction of the function h of x1, x2, xn, the given nonlinear programming problem can be written as z equal to f of x subject to the constraint h of x less than or equal to 0, x greater than or equal to 0. Now, we introduce a new variable s, so that this inequality constraints can be converted into equality constraints by the way of defining minus h of x equal to s square or h of x plus s squared equal to 0. This new variable s is called slack variable. We introduce such slack variable for the purpose of converting this inequality constraint into equality constraints. Now, by the way of defining minus h of x equal to x squared, the LPP can be rewritten in this way. This is the modification of the original nonlinear programming problem, optimizing z equal to f of x subject to the constraint h of x plus s squared equal to 0, x greater than 0. Here the variable s is called slack variable. We introduce slack variable to convert the inequality constraints into equality constraints. This slack variable appears in the form of s squared in the constraints. By this, the slack variable ensures that this variable is non-negative. So, by introducing the slack variable s in the inequality constraints, that inequality constraint become equality constraint, which becomes h of x plus s squared equal to 0, x greater than or equal to 0. Now, this modified nonlinear programming problem is in terms of n plus 1 variables with a equality constraints. We know very well that any nonlinear programming problem with equality constraints can be solved using Lagrangian functions. Now, the NLPP involving n plus 1 variable with equality constraints can be easily solved by making use of Lagrangian multiplier method. Now, for this nonlinear programming problem, the Lagrangian function is L of x s, where s is a slack variable, and lambda equal to f of x minus lambda into h of x plus s squared. So, this nonlinear programming problem can be solved with the help of Lagrangian function. The Lagrangian function for this nonlinear programming problem is L of x s lambda equal to f of x minus lambda into h of x plus s squared. So, the Lagrangian function is f of x minus lambda into h of x plus s squared. Now, the stationary point can be obtained by the following conditions. The first condition is dou L by dou x equal to dou f by dou x minus lambda into dou h by dou x. If it is in terms of more than one variable, we will rewrite it as dou L by dou x j equal to dou f by dou x j minus lambda into dou h by dou x j. J varies from 1 to n. Now, the second one is dou L by dou lambda, which we have minus of h of x plus s squared. We take it as the condition dou L by dou x j equal to 0 and dou L by dou lambda equal to 0, we will get this equation, and the final one is dou L by dou s, which we have the partial derivative of this function with respect to x, we have minus 2 s lambda equal to 0. We consider this as equation 1, this as 2 and this as 3. So, the partial derivative of this function with respect to x and lambda and s leads to these 3 equations. Now, these 3 equations gives the necessary condition for solving a nonlinear programming problem. Now, from equation 3, we have either lambda equal to 0 or s equal to 0. If we consider s equal to 0, then from equation 2, we have h of x equal to 0. Now, from equation 2 and 3, we have lambda into h of x equal to 0. So, by making use of equation 2 and 3, we will get the equation as lambda into h of x equal to 0, we name it as equation 4. Now, the slack variable is introduced merely to convert the inequality constraint into equality constraints. Moreover, since s squared is non-negative, we have h of x is less than or equal to 0. So, from these 3 conditions, we will get the condition as dou L by dou x j equal to dou f by dou x j minus lambda into dou h by dou x j, and from equation 2 and 3, we have lambda into h of x equal to 0 and h of x less than or equal to 0. Of course, we know very well that lambda is greater than or equal to 0. So, from the Lagrangian function, the necessary condition for identifying the stationary point is dou L by dou x j equal to dou f by dou x j minus lambda into dou h by dou x j equal to 0, and dou L by dou lambda equal to minus of h of x plus s squared equal to 0, and dou L by dou s equal to minus 2 s lambda equal to 0. Now, from the equation 2 and 3, we will get the additional constraint as lambda into h of x equal to 0 and h of x less than or equal to 0 and lambda greater than 0. Now, whenever h of x less than 0, our lambda takes the value 0, and whenever lambda greater than equal to 0, our h of x takes the value 0. Therefore, we can say that lambda is unrestricted with the signs. So, from this necessary condition, we will get the following conditions. Those conditions are called Hundaker conditions. Now, Hundaker condition for a nonlinear programming problem which maximize f subject to the constraint h less than or equal to 0 is f j minus lambda h j equal to 0, j varies from 1 to n. Here f j means partial derivative of f with respect to the decision variable x j, and h j is partial derivative of the function h with respect to the decision variable x j, j varies from 1 to n. So, the first condition f j minus lambda h j equal to 0, and the second condition is lambda h equal to 0, and the third condition is h less than or equal to 0, and fourth condition is lambda greater than or equal to 0. So, for a nonlinear programming problem which maximize f subject to the constraint h less than or equal to 0, we will get these four conditions. These four conditions are called Hundaker conditions. Now, the Hundaker condition is f j minus lambda h j equal to 0, lambda h equal to 0, and h less than or equal to 0, and lambda greater than or equal to 0. This is the Hundaker condition for a nonlinear programming problem in which the objective function is maximum z and the set of constraint is h less than or equal to 0. Now, in a similar manner, we can obtain the Hundaker condition for a nonlinear programming problem in which the objective function is minimum and subject to the constraint g of x greater than or equal to 0. As usual, now by taking our function h of x equal to g of x minus c, this constraints can be written as h of x greater than or equal to 0. Therefore, the given nonlinear programming problem becomes minimum z equal to f of x subject to the constraints h of x greater than or equal to 0 and x greater than or equal to 0. So, by this introduction of h of x, the given nonlinear programming problem can be written as this way. Now, by introducing a surplus variable s naught into this constraints, this inequality constraint can be rewritten in terms of equality constraints. Therefore, the given nonlinear programming problem can be modified in the following way, which can be written as minimum z equal to f of x subject to the constraints h of x minus s naught squared equal to 0 and x value greater than or equal to 0. This s naught is called surplus variable. By introducing this surplus variable in this constraint, this inequality constraint becomes equality constraint. Again, this is the problem involving n number of decision variable with a equality constraints. Now, we can easily solve this problem by considering Lagrangian function for this problem. Now, the Lagrangian function for this problem is L of x comma s naught comma lambda is f of x minus lambda into h of x minus s naught squared. Now, for this nonlinear programming problem, the corresponding Lagrangian function is this one. Now, with this help of this Lagrangian function, easily we can get the necessary condition, which is nothing but f j minus lambda h j equal to 0, lambda h equal to 0, h greater than or equal to 0, lambda greater than or equal to 0. So, for the given nonlinear programming problem which minimize z equal to f of x subject to the constraint h greater than or equal to 0, the corresponding Hundaker conditions are f j minus lambda h j equal to 0, lambda h equal to 0, h greater than or equal to 0 and lambda greater than or equal to 0. Let us have a break. Welcome back. Before break, we derived the Hundaker condition, that is necessary condition for solving a nonlinear programming problem with inequality constraints. Now, with the help of this necessary condition, that is using Hundaker condition, we try to solve a nonlinear programming problem with involve single inequality constraints. Consider the problem: maximize z equal to 3.6 x 1 minus 0.4 x 1 square plus 1.6 x 2 minus 0.2 x 2 square, subject to the constraints 2 x 1 plus x 2 less than or equal to 10, x 1 x 2 greater than or equal to 0. So, the given nonlinear programming problem involving two decision variable x 1 x 2 with a single inequality constraints. Now, this problem can be solved easily by converting this inequality constraints into equality constraints. Now, by converting this inequality constraints into equality conditions, we got the Hundaker condition, which is necessary condition for solving this problem. The Hundaker condition for this problem is f j minus lambda h j equal to 0. This is the first condition, and the second condition lambda h equal to 0. The third condition h of x less than or equal to 0, and the final condition is lambda greater than or equal to 0. So, the Hundaker condition to solve this problem is f j minus lambda h j equal to 0, lambda h equal to 0, h of x less than or equal to 0, lambda greater than or equal to 0. Now, by making use of this Hundaker condition, we will try to maximize the objective functions. Now, for the given problem, our f of x is 3.6 x 1 minus 0.4 x 1 square plus 1.6 x 2 minus 0.2 x 2 squared, and the given constraint is g of x is 2 x 1 plus x 2 less than or equal to 10. Now, by taking g of x minus 10 as h of x, we have h of x is 2 x 1 plus x 2 minus 10. Now, the given nonlinear programming problem involving a inequality constraints. Now, the necessary condition for this given nonlinear programming problem is Hundaker condition. The first condition is f j minus lambda h j equal to 0. Now, this condition gives us the partial derivative of the function with respect to x 1, which we have 3.6 minus 0.x 1 equal to lambda h 1. So, lambda into the derivative of h of x with respect to x 1 is 2. So, we have lambda into 2, otherwise 2 lambda. Then the partial derivative of this function with respect to x 2 is 1.6 minus 0.4 x 2 equal to the partial derivative of this function with respect to x 2 is 1. So, 1 into lambda, we have lambda. So, the first condition f j equal to lambda h j equal to 0 implies the two equation. The first one is dou f by dou x 1 minus lambda into dou h by dou x 1 gives the first equation, and dou f by dou x 2 minus lambda into dou h by dou x 2 gives the second equation. Now, the second Hundaker condition is lambda h equal to 0. The condition lambda h equal to 0 gives us lambda into our h is this one. So, 2 x 1 plus x 2 minus 10 equal to 0. We name it as equation 3. The third Hundaker condition is h less than or equal to 0. So, we have h less than or equal to 0 imply 2 x 1 plus x 2 minus 10 less than or equal to 0. We name it as equation 4. Of course, the constant Lagrangian multiplier lambda greater than or equal to 0, we have equation 5. So, from the Hundaker condition f j minus lambda h j equal to 0, lambda h equal to 0, h less than or equal to 0 and lambda greater than 0, we have these 4 equations. Now, from equation 3, we have either lambda equal to 0 or 2 x 1 plus x 2 minus 10 equal to 0. From equation 3, we have either lambda equal to 0 or this equation 2x1 plus x2 minus 10 equal to 0. Suppose if we assume lambda equal to 0, we consider the case lambda equal to 0. If lambda equal to 0, then equation 1 and 2 becomes 3.6 minus 0.8 x1 equal to 0. From this we have x1 value equal to 4.5. Now, by substituting this x1 value in this equation, we have x2 equal to 4. Now, with this value of x1 x2, if we substitute this x1 x2 in equation 4, we have 2 into 4.5 which is 9 plus 4 which is 13 minus 10 which is 3, not satisfied this equation. So, with this value of x1 x2, equation 4 not satisfied. Therefore, this value, this x1 x2 cannot give the optimum value of the given objective functions. Therefore, we should omit this value. Now, for the case lambda equal to 0, we got the value of x1 x2 as 4.5 and 4. For this value of x1 x2, equation 4 is not satisfied. Therefore, we cannot get the optimum solution for the given nonlinear programming problem for the case lambda equal to 0. Now, we consider the other case. Now, consider the case 2x1 plus x2 minus 10 equal to 0. From this equation, we have x2 equal to 10 minus 2x1. Now, consider the first two equations. From the first two equation, we have 3.6 minus 0.x1 equal to 2 into, by making use of this equation, instead of lambda, I will substitute 1.6 minus 0.4 x2. Now, this equation can be written as 3.6 minus 0.x1 equal to 3.2 minus 0.8 x2. Now, we simplify this equation and rewrite it properly, which we have 0.8 x1 minus 0.8 x2 equal to 0.4. Now, in this equation 0.8 x1 minus 0.8 x2 equal to 0.4, I will make use of the value of x2, x2 equal to 10 minus 2 x1. So, this equation can be rewritten as 0.8 x1 minus 0.8 into 10 minus 2 x1 equal to 0.4. Now, again if we simplify this equation, we have 0.8 x1 minus 8 plus 1.6 x1 equal to 0.4. Now, from this equation, we have our x1 value is 8.4 by 2.4, which we have 3.5. Now, by simplifying this equation, we have x1 equal to 8.4 by 2.4, which we have 3.5. Now, by substituting this x1 value in this equation, we can get the value of x2, where x2 equal to 10 minus 2 into 3.5, which is 7. So, 10 minus 7, 3. So, for this problem, the stationary point x naught gives the value of 3.5 comma 3. So, for this value, we get the optimum value of the objective function. Now, with this x1 equal to 3.5 and x2 equal to 3, the maximum f of x value is 10.7. So, maximum z equal to 10.7. So, with the help of Hundaker conditions, the objective function which takes the maximum value for the value of x1 equal to 3.5 and x2 equal to 3 is 10.7. Let me recap. A given nonlinear programming problem with single inequality constraints can be easily solved with the help of the necessary condition, which we called as Hundaker conditions. If the objective function is maximum and the constraint subject to the constraints h less than or equal to 0, then the corresponding Hundaker condition is Fj minus lambda Hj equal to 0 and lambda H equal to 0, H less than or equal to 0, lambda greater than or equal to 0. Now, the corresponding Hundaker condition, if the objective function is minimum subject to the constraint h greater than 0 is Fj minus lambda Hj equal to 0 and lambda H equal to 0, H greater than or equal to 0 and lambda value greater than or equal to 0. Here j varies from 1 to n. The question is, solve the nonlinear programming problem minimize z equal to 6x1 squared plus 5x2 squared subject to the constraints x1 plus 5x2 greater than or equal to 3, x1 x2 greater than or equal to 0. So, the given function is minimum z with respect to the constraint h greater than 0. Now, for this problem the corresponding Hundaker condition is Fj minus lambda Hj equal to 0, lambda H equal to 0, H greater than or equal to 0, lambda greater than or equal to 0. So, with this help of the Hundaker condition, we can obtain solution for this nonlinear programming problem. Thank you.